Welcome back, everyone. Ready for another deep dive.
Always.
Today we're going high-flying, exploring the world of aircraft metals.
Ooh, that's a good one.
Yeah, we've got this handbook for aircraft maintenance technicians. It's actually really fascinating, even if you're not, you know,
Yeah,
an engineer.
right. It's amazing how much you can learn from these technical manuals.
Yeah, and this one starts off right away
Yeah.
with this emphasis on how important the materials are.
Absolutely. The stakes are incredibly high in aviation. I mean, they make it clear from the very beginning, even a tiny deviation from the specified materials, a seemingly insignificant substitution,
Mhm.
that could lead to, well,
Catastrophic
okay,
consequences.
we're talking about situations where lives are on the line.
It's a powerful reminder, isn't it?
Yeah.
That the wrong material can completely undermine even the best craftsmanship.
It really is. And it's a principle that applies, well, beyond aviation, too.
Oh, absolutely. Any field where quality and attention to detail matter,
All right.
which is pretty much every field. So this handbook, it kind of lays out a metal properties 101. They talk about
Yeah.
toughness versus brittleness.
That's a fundamental one.
I think we can all relate to this.
Oh, really?
Toughness, it's like,
Like a gymnast.
yeah,
They can bend and twist and withstand all kinds of forces without breaking.
yeah. Or like a martial arts master, right? Taking those blows.
Exactly.
But brittleness, that's like,
A dry twig,
hmm.
snap. It just breaks under the slightest pressure.
And in an aircraft, obviously,
You don't want brittleness.
you need that toughness, right?
Absolutely. Think about an aircraft wing flexing during turbulence. You need a material that can handle those stresses without cracking. Otherwise,
Well, it doesn't bear thinking about it.
and then they go into stress and fatigue.
Right.
So stress, I kind of get that. That's like the force you're putting on something, right?
Wow.
But fatigue, that's a little trickier. Yeah. Fatigue is the weakening of a material due to repeated stresses over time. Think of it like bending a paper clip back and forth. Each bend might seem tiny, but eventually,
It breaks.
exactly, those repeated stresses cause microscopic cracks to form and grow. And
I
eventually,
just can't take it anymore.
right. And that's why regular inspections and maintenance are so crucial for aircraft. They're looking for those tiny cracks before they become major problems.
So it's all about catching those early warning signs.
Okay.
Okay, so diving into the actual metals. They start with ferrous metals. And I think that just means they contain iron, right?
That's it. The Iron Age of flight.
But it's not just plain old iron, is it?
No. We're talking about steel alloys. They take iron and add small amounts of other elements like nickel, chromium, molybdenum. And these additions, they completely change the properties of the steel.
So it's like they're fine-tuning the recipe to get the exact properties they need.
Exactly. For instance, adding nickel increases strength and elasticity. Chromium boosts toughness and corrosion resistance. It's all about creating the perfect metal for the job.
So how do they even figure out what's in these different types of steel?
They use a technique called spark testing. It's pretty cool, actually. When you grind a piece of steel, it creates sparks.
Oh, yeah. I've seen that.
And the pattern, the color, the shape of those sparks, it reveals the composition of the steel. It's like a fingerprint.
So they can tell just by looking at the sparks. That's amazing.
It is. And then they break down steel by its carbon content. Low, medium, and high carbon steel, each with its own unique properties and uses.
So low carbon steel, that's for like less demanding applications, right?
Exactly. Think nuts, bolts, safety wire, bushings. Those small but essential parts that hold everything together.
Yeah, gotta have those. And then medium carbon steel, what's that used for?
That's where you need a bit more strength and machinability. Forged parts, machined components, things that need to be precisely shaped and able to handle some stress.
And then you've got the heavy hitter, high carbon steel.
Right. Springs, for example. They need incredible strength and resistance to wear and tear.
So low to high carbon, it's like a hierarchy of strength.
You got it. And to make sure everyone's speaking the same language, they use these standardized SAE numbers to identify the specific steel compositions.
Oh, that makes sense. Like a universal code for steel.
Exactly.
And then there were these like alloy superstars, nickel steel, chromium steel,
Molybdenum steel.
each with its own unique contribution.
Absolutely. Like nickel steel, it combines strength and elasticity without sacrificing flexibility.
It's like the perfect blend of, being tough but not brittle.
Exactly.
And then chromium steel.
That's your toughness, strength, and corrosion resistance all in one.
The trifecta.
They use it in bearings, those tiny but essential components that have to withstand constant friction and wear.
So it's got to be super durable.
It does.
And finally, chrome molybdenum steel,
The welding champion. This one can handle the heat and stress of welding without becoming brittle.
which is important for, building and repairing those massive aircraft structures.
Absolutely. Welding allows for modular construction, easier repairs. It's essential.
Okay, we've explored the world of ferrous metals, those iron-based powerhouses. But what about the other side of the coin? The non-ferrous metals.
Ah, yes. Where things get even lighter,
Yeah.
literally.
Yeah. I'm ready to lighten things up. Let's dive into that world.
Let's do it. So, stepping into the realm of non-ferrous metals, this is where we really start to see the focus on minimizing weight without compromising strength. And I think the most prominent example, the real champion here, has got to be aluminum.
Aluminum. Yeah, it seems like it's everywhere, right? Cans, foil, even those water bottles everyone seems to have these days.
Right. And it's not just lightweight, although that is a major advantage when you're trying to, well, get a massive hunk of metal up into the air. Aluminum is also incredibly malleable, easy to shape.
Oh, right, malleable. It's like, what, you can bend it easily?
Exactly. And it's ductile too. That means you can stretch it out without it breaking.
So it's got that flexibility. Okay, that makes sense. So lightweight, flexible, I can see why that'd be appealing for aircraft. All those sleek aerodynamic shapes.
Absolutely. And on top of that, it has excellent corrosion resistance, which is crucial when you consider the environment aircraft operate in.
Right, makes sense. So aluminum sounds pretty amazing,
Mm.
but isn't there like different types of aluminum? I know the handbook mentions these aluminum alloys.
You're right. It's not just a one-size-fits-all situation. Just like with steel, they add small amounts of other elements to aluminum to create these alloys with specific properties.
So it's like you're tailoring the aluminum for different jobs.
Precisely. For example, adding copper to aluminum makes it incredibly strong. So you'll find those copper aluminum alloys in high-stress areas of the aircraft, like the wings, the fuselage.
Ah, so it's like the muscle of the aircraft.
Mm.
But I remember the handbook did mention something about these copper aluminum alloys needing like extra care to prevent corrosion.
That's right. Aluminum on its own is naturally corrosion resistant, but sometimes those alloying elements, they can make it a bit more susceptible, especially in harsh environments.
So it's a trade-off. You get the strength, but you might have to take some extra steps to, what, protect the metal from the elements?
Exactly. They use coatings, special surface treatments, things like that to prevent corrosion from taking hold.
Okay, so they're basically, what, giving the metal a shield.
That's a good way to put it. And then there's the whole concept of heat treating aluminum, which is really fascinating.
Heat treating, is that like what, baking the metal?
It kind of is. They carefully heat and cool the metal to change its internal structure.
And how does that actually change its properties?
Well, remember when we talked about those grains, those tiny crystals within the metal?
Oh, yeah?
Heat treating can actually rearrange those grains, making them smaller and more tightly packed, and that increases the metal's strength and toughness.
So it's like reorganizing the building blocks of the metal.
Exactly. And they can do this to make aluminum stronger, harder, even more flexible, depending on what they need.
So it's like customizing the aluminum for the job.
Yeah.
Okay, aluminum, that's pretty impressive. Light, versatile. But what about magnesium? Isn't that even lighter than aluminum?
You bet it is. Magnesium is incredibly light. It's like 2/3 the weight of aluminum.
Wow. So why isn't everything made of magnesium if it's that light?
Well, there's a trade-off. Pure magnesium on its own, it's not strong enough for those structural parts in aircraft. They have to mix it with other metals to create alloys that are, well, sturdy enough.
So it's a balance. You get the lightness, but you might have to compromise on strength.
You're right. And there's one other thing to consider with magnesium. It can be flammable.
Oh, okay. Yeah, that's probably not ideal for an airplane.
Not so much. But it does have its advantages. You know, they used magnesium in the past for parts like nose wheel doors, flap covers, things that benefited from being really light without needing that super high strength.
Makes sense. So we've got aluminum, the lightweight champ,
Mhm.
and magnesium, the super featherweight contender. What about titanium? I always hear about titanium being this like super metal.
It is pretty amazing. Titanium sits kind of in between aluminum and steel in terms of that strength to weight ratio.
Oh, okay. So lighter than steel, but stronger than aluminum.
You got it. Plus, it can handle the heat. Titanium has a really high melting point, so it's ideal for components that are exposed to those higher temperatures, like parts of the engine.
Strong, light, and heat resistant. What's not to love?
Well, even titanium has its limits. Its strength can decrease at those very high temperatures, and if it's exposed to heat for a long time, it can become brittle.
Yeah.
But overall, it's an incredibly versatile material, really desirable in aircraft construction.
And corrosion resistant,
Oh,
too.
absolutely. That's a big one, especially in an environment where you're constantly battling the elements.
Okay, so aluminum, magnesium, titanium, those are the big players in the world of aircraft metals. What about copper? I kind of always think of wiring when I hear copper, but I guess it's more than just that in aircraft, right?
It is. Copper is best known for its electrical conductivity, hence all the wiring. But it's also a great heat conductor,
Oh, right.
so it's used in heat transfer applications as well. And then you have things like beryllium copper. It's a special alloy that becomes incredibly strong after heat treating. They use that in parts that need to withstand a lot of wear and tear, things like diaphragms, bearings, springs.
Wow, okay, so copper is a pretty versatile player in the aircraft world. But with all these different metals and alloys, how do they even decide which one to use for a particular part?
That's where the expertise of materials engineers comes in. It's a complex decision-making process. They have to think about the strength, the weight, the corrosion resistance, even the cost of each material. It's like solving a really intricate puzzle, making sure each piece of the aircraft has the right material.
It's all about finding that perfect fit.
Yeah.
And the handbook, it stresses this idea of, consulting the manufacturer's documentation when it comes to substituting metals during repairs. Sounds like you really don't want to mess around with that delicate balance of an aircraft.
You're absolutely right. Aircraft are complex machines, and even small changes can have big consequences.
So it's not just about fixing the problem, it's about understanding how that fix might affect the entire aircraft.
Precisely. And that's why there are such strict regulations and guidelines when it comes to aircraft maintenance and repair. It's all about ensuring safety.
Okay, so we've covered the basics, the key properties of metals, dived into some specific examples. But how do they go from those raw materials to the actual parts and structures that make up an airplane? How do they transform that chunk of metal into like a sleek aerodynamic wing?
That's where the art of metal forming comes in. And that's a whole other world of fascinating techniques and processes.
Sounds like we need another deep dive. Let's explore that world. So we've talked about choosing the right metals for the job, fine-tuning their properties with those heat treatments. But how do they actually shape those raw materials, those hunks of metal, into the intricate parts that make up an airplane?
It's quite a process. They use a variety of techniques, and each one is, well, it's suited for creating different shapes and achieving different results. One of the most fundamental techniques, though, is forging.
Forging. Okay, so like a blacksmith hammering away at a piece of hot metal.
Exactly. It's like sculpting, but with metal. And they use different types of forging to achieve different results, like drop forging, for instance. They use a heavy hammer to force the metal into a die, which is basically a mold, and that creates a precisely shaped part.
So it's like really forcing the metal to take on the exact shape you need. But forging does more than just shape the metal, right? Doesn't it also make it stronger?
It does. Remember when we talked about those grains, those tiny crystals that make up the metal?
Yeah.
Well, the forging process, it actually rearranges those grains, making them smaller and more tightly packed together.
So it's like you're strengthening the metal from the inside out. Okay, forging, that's pretty cool.
hmm
What are some of the other methods they use for shaping metal?
Well, there's drawing, which involves pulling a metal through a die to reduce its diameter or create a specific shape. Think of it like squeezing toothpaste out of a tube.
Ah, okay. So that's how they make those really long, thin wires for the electrical systems.
Exactly. And tubes for hydraulic lines and other fluid carrying components. And then there's extruding. That's where they push the metal through a die to create a specific shape. It's similar to drawing, but it's more about squeezing the metal into the desired form.
So you can create more complex shapes with extruding.
You can. They use extruding to make all sorts of structural components, channels, angles, beams, and aluminum, because it's so workable, it's a great metal for extruding. So yeah, you can get some pretty complex shapes that way.
Okay, so metals are obviously the stars of the show when it comes to aircraft construction. But the handbook, it does mention some non-metallic materials as well, like wood, for example.
Ah, yes, wood, the original aircraft material. Of course, its use has drastically declined, especially since, the mid-1950s. But it still has its place.
Yeah, it's hard to imagine a modern jetliner made entirely out of wood.
hmm
But I guess for those smaller aircraft, maybe those home-built ones, it still makes sense, right?
Right. It's lightweight, it's easy to work with, and, there's something kind of, well, nostalgic about using wood in aircraft. It's a nod to those early pioneers of aviation.
Definitely. So wood is still hanging in there, at least in certain niches. What about those newer, more high-tech materials? The handbook mentioned composites. Aren't those becoming more and more common in aircraft?
Absolutely. Composites are amazing materials. They're like custom designed to combine strength, lightness, and flexibility in ways that you just couldn't achieve before.
So it's like taking the best properties of different materials and they're like merging them into one.
Exactly. And what's really cool is how they make composites. They basically take fibers like glass or carbon fibers and embed them in a resin matrix.
Fibers and resin.
Yeah, so the fibers, they provide the strength, and the resin, it holds everything together.
It sounds almost like weaving a fabric, but with these high-strength materials.
It's a bit like that. And this combination, these fibers and resin, it gives composites that incredible strength to weight ratio, and they're also very resistant to corrosion.
It sounds almost futuristic, like something straight out of a sci-fi movie. So where are they using these composites in aircraft?
They're using them all over. Wings, fuselages, tail sections, even landing gear components. And as the technology keeps advancing, we're probably going to see composites playing an even bigger role in aircraft design in the future.
It's really amazing to see how material science is changing the way aircraft are built. Okay, so we've talked metals, composites, even wood. But what about something as basic as rubber? Does that have a place in aircraft?
It does. It might not be as structurally prominent as, say, the metals, but rubber is crucial for sealing, for cushioning, for providing flexibility in a lot of different systems in the aircraft.
Okay, so like gaskets, seals around the doors and windows, maybe even those little tray tables.
Exactly. And they use different types of rubber depending on what they need. Natural rubber, synthetic rubber, even silicone rubber. Each one has its own unique properties. Like natural rubber, it's really good for shock absorption, while silicone rubber can handle those high temperatures.
So it's not just rubber, it's like a whole family of rubbers. Okay, we've covered the materials themselves, but what about all the things that hold those materials together? Like the nuts, bolts, rivets, all that hardware. It's got to be pretty important too, right?
Absolutely. That's what we call aircraft hardware. It's the unsung hero of aviation. And it's a world of its own. You've got your threaded fasteners like bolts and screws. They're essential for joining parts that might need to be taken apart later, for maintenance or repairs.
Right. And I remember the handbook talking about something called safety wire. What was that all about?
Ah, yes, safety wire. It's like a little safety net for your fasteners. They use it to prevent nuts, bolts, even those little cotter pins from loosening up due to all that vibration and those forces that the aircraft experiences during flight.
So it's like a simple but effective way to keep things from, well, falling apart mid-flight.
Exactly. They use it on all sorts of components, turnbuckles, oil caps, you name it. And then you've got rivets. They might seem pretty straightforward, but there are actually a lot of different types of rivets. Solid rivets, blind rivets, even those high-strength rivets that they use in the really critical structural areas.
So there's a rivet for every job.
Pretty much. And the handbook, it even goes into how to repair those holes if they get damaged. A damaged hole can compromise the whole structure.
Oh, right. So it's not just about putting the parts together. It's about making sure those connections are strong and reliable.
Exactly. And then you have to think about how they control those moving parts, like the ailerons, the rudders, the elevators, those things that help the pilot maneuver the aircraft.
Right, right.
They use these things called control cables and terminals for that. Think of those cables as the nerves of the aircraft. They transmit the pilot's commands to the control surfaces, making sure the aircraft responds the way it should.
So they're like the communication lines between the pilot and the
Exactly. And they make those cables from really strong materials like carbon steel or stainless steel. They have to be able to withstand a lot of force without stretching or breaking.
Yeah, that makes sense. What about adjusting the tension on those cables?
They use turnbuckles for that. They're these mechanical devices that allow for really precise adjustments. And of course, they safety wire those turnbuckles too, just to be extra sure they don't come loose.
So it's like every little detail, every connection, it's all carefully considered and addressed.
It really is. Aircraft construction is all about precision, about attention to detail. Every single part, every fastener, every piece of material, it plays a role in ensuring the safety and reliability of the aircraft.
Well, this deep dive has really opened my eyes to the world of aircraft materials. It's amazing to see how much thought and engineering goes into something that we often take for granted.
It's pretty incredible, isn't it? From those basic properties of metals to those advanced composites, and even those humble but essential components like rubber and rivets, every single element has a story to tell, a role to play.
It's like A symphony of materials all working together to create these incredible machines that can soar through the sky.
That's a great way to put it. And next time you see an airplane flying overhead, I hope you'll think about all those hidden wonders, all those materials that make it all possible.
I definitely will. Thanks for taking us on this incredible journey. It's been fascinating.
My pleasure. It's always a joy to share my passion for aviation. And to all our listeners out there, thanks for joining us on this deep dive. Until next time, keep exploring, keep learning, and keep looking up.